Okay, good afternoon, everybody. We are going to get started with our presentations for the afternoon. We have three wonderful speakers lined up who are going to talk to us on the subject area of the road to carbon neutrality. So our first speaker today is Dr. Mario Tenura. His training includes a Bachelor of Science in Botany and Physical Geography, a Master of Science in Soil Science, and a PhD in plant sciences, and a postdoctoral research in nematology. So together with many colleagues and collaborators, his team are researching many soil-related issues, including controlling potatoes, early dying, improving nitrogen use efficiency of crops, mitigation of greenhouse gas emissions from fertilizers, development of rapid molecular tests of emerging soil-borne diseases and nematode pests, and improvement of soil health. So Mario is the lead of the Canadian Potato Early Dying Network. So welcome, Mario. And with that, I think you can take it away.
Happy St. Patrick's Day, everyone. And I'm very pleased to have our chairperson for today's session being a true Irish person. So this is fantastic. I feel very lucky today. This is excellent. So Road to Carbon Neutrality, a research perspective to be followed by producer perspective, and then also by a market or industry perspective. And I'm going to really largely going to be taking off from where Dr. Cantor was yesterday, and so we're going to be really talking about nitrogen a lot here. That doesn't mean yet the carbon side of things, the methane and carbon dioxide, are not as important. It's just that 20 minutes we just can't do it all. So the near road, so the short-term road, what do we have in store for us? Well, the government of Canada has committed to reduction in N2o emissions from fertilizers by 30% below 2020 levels by 2030. So it's 8 years from now. This is really a game changer for us in agriculture. This is the first time agriculture has been included in reduction emission targets in Canada. And as Dr. Cantor said yesterday, he was unaware of agriculture, except he gave one example, which I forget the country, that agriculture had been committed to for reductions. Well, we're probably the second one there, and it's particularly pinned on fertilizers and reduced N2o emissions. Now, can we do it? And I said that to myself, and the first thing that popped up was Bob the Builder. Of course, yes, we can. You know, him, Wendy, and the whole gang. Let's see, can we do it? Well, firstly, what's the big huff about N2o and agriculture? Well, I don't need to tell you N2o is a greenhouse gas, but issue is major source of N2o is from agriculture, okay? CO2 and extent of methane as well. There's a lot of other sectors of the economy contributing to that gas, but for us, we're, as an agriculture, major producer of N2o. Here's an example of Saskatchewan. 55% of the greenhouse gas emissions from Saskatchewan are N2o. Okay, and then methane. So we're really looked at to contribute to this reduction. I guess the government's perspective is to share the burden, if you will, or share the contribution to the reduction targets. So we've been targeted now in the near road for N2o. So let's see what we can do about that. So our team has really been looking at the 4 Rs, which is a framework to have our farmers to use, and their crop consultants to use, and also for me as researchers, to use to come up with the best suite of nitrogen management practices. Now, it seems simple. You choose the right rate of fertilizer for your crop. You choose the right product or source of nitrogen for your crop. You choose where to place it that's best for the crop to take up that nitrogen, and when to apply it for the timing. It's way more complicated when we get into reality of managing a crop in the field, because we deal with weather conditions, different soil conditions in terms of the wet soils, dry soils, soils that are not tilled, that are tilled, soils with perennial cover, non-perennial cover. It gets very complicated. So that's why I call it a framework. This isn't set in stone. This is the magic recipe for managing nitrogen, because that's always going to change, okay? But it's a fluid decision-making process, okay? And so we've been working with the 4Rs in terms of trying to tackle the reductions in N2o. One of the things that's really popped up recently, in the past 10 years or so, is the advent of new nitrogen fertilizer sources. So these are formulations of our tried and true, some of our tried and true nitrogen products, such as urea, for example, or anhydrous ammonia, UAN, and they have additives to them. And the additives being inhibitors of urease enzyme activity. That's the enzyme that breaks down urea to convert it to ammonia. So nitrification inhibitors, which target the biochemical machinery that specific group of bacteria have to conduct nitrification. And then there are some products that have both the two combined together. And these products are now giving farmers some flexibility, and show you flexibility in terms of, with the 4Rs, to be able to reduce nitrogen losses. Now, this is the we can do it slide, okay? So this is a summary. It feels like a summary of a life's work in our lab. It's a summary of our N2o studies. Not all of them, but most of them, and related with 4R since 2010. So we have different practices. In the left column, number of site years, and most of my experiments are done on farm fields, actually farmer fields. Give an idea of the reduction in N2o that was averaged across those experiments or site years, and then what's been the impact on yield, okay? So right off the bat, showing you here that there's this trinity here of three reduction practices: polymer coated urea, nitrification inhibitors, and split nitrogen application, resulting in fairly high 30 to 50% reduction in N2o emissions from a business as usual or a conventional practice. So for example, nitrification inhibitors, it would be using urea without inhibitors, for example, okay? And the polymer coated urea is urea, conventional urea that's coated with a very, very thin polymer plastic that slows down the release of the urea. That seems to be enough that's slowing down to reduce N2o emissions in most of our, well, in our studies that we've done. Nitrification inhibitors, equally as effective in reducing N2o emissions, 30% reduction. Now, split nitrogen application, we're putting down some of the nitrogen at planting and some halfway through the season, almost 50% reduction in N2o emissions. That is pretty considerable. And really, that is 30% of what we need in terms of reduction. So there's really, we have some tools available to us to meet that near-term target, which is pretty fantastic. Now, some other practices. One, for example, which actually goes the wrong way, which is shallow banding, which is putting fertilizer in a very shallow band. So that's like half an inch to an inch below the surface. Nitrogen, that actually increases N2o emissions. So that's practice that is becoming more popular with small seeded crops. So this is something that we have to be careful with, and it's going to be a practice that we're going to need to deal with to not encourage so much, actually, or find remediations around it. Well, one remediation that we've seen is to use the nitrification inhibitor in these shallow bands, and that will snuff out the increase in N2o emissions quite well, actually. Another is using nitrogen fixing legumes. So if we grow alfalfa, field pea, soybean, faba, they produce their own nitrogen. They reduce emissions by half from a field. And in reality, they're actually bringing emissions down to almost nil in terms of from background. So when they say reduced by 56%, really what's left for emissions is what the soil would naturally produce anyway without adding fertilizer, okay? So legumes are phenomenally effective, okay? But something like fall application of fertilizer actually increases N2o. So this is going in a direction that isn't good for us, of course. Some practices or management, such as organic production, decrease in N2o, about 17% in terms of one study that we did over 2 years. And now they're looking at cover crops that survive over winter in Manitoba. No change in N2o emissions. Actually, that's a good thing, because we were concerned that maybe the death of the cover crop would encourage, feed the microbes to produce N2o, but it's not the case. So that's actually a good thing. So we can have that benefit of that carbon and that soil health benefit of the cover crops. Now look at the yields. Nothing in terms of these practices. And this is very typical. We see a very good environmental benefit to these practices, but yet we do not see direct yield benefit most of the time. Really, it's talking about environmental benefits here. It's quite different than we've been thinking in the past, which is about production, yield. Thinking here in terms of these practices about nitrogen management from the standpoint of reducing environmental consequences. Organic production did reduce N2o, but it also had a yield hit. So it hasn't been, we need to be working on that to improve the yield so that it can be more competitive, I guess, in terms of N2o reductions and conventional practices. Let me show you now, we need some room for improvement though. Here in green is ESN and Super U. So these are those products that reduce emissions by 30–50%. The uptake in Canada, in the prairie provinces is less than 10%. Less than 10% of the fertilizer used are these products. This is over 5 years worth of data. Okay, so there's a lot of room for improvement here, and obviously then there's room for N2o emissions reduction. That's why I think it's not going to be a challenge to get us to that 30%. It's really a matter of the adoption of the practices and encouraging the use of the products. And here's an example of an encouragement for a farmer. The break-even point to pay for those special fertilizers, because they cost a little bit more than about 10%, 10–15% more than the conventional fertilizer like urea. They can either target more yield, and in this case, it shows you how much yield in grain corn would need to compensate for the costs of those special products. Okay, 4 to 2.5 bushels. A lot of farmers will say, well, I'm sure I can do that with my better management practices. Do they actually get that? I'm not quite sure, but a lot of them will target that. Other alternative, of course, is to use markets. And so I'll briefly mention that, but Alex is going to really talk much more about that. So, but we do need economic incentives required for adoption of these inhibitors. Why? Because they're more costly. And the farmer banks on more yield, or they're going to need to be compensated for using those products. Maybe something related with Dr. Cantor was saying, spread out the burden. Maybe the farmer doesn't have to pay for the fertilizer. Maybe it should be through the whole food system. Here's a break-even point now for using these products, these inhibitor-based products, in terms of on a carbon market. If a farmer in the dark brown or the black soil zones on the prairies a farmer using the inhibitors to reduce N2O in the black, so around Winnipeg and so forth, $78 a ton if they were to play the market, a carbon market. Well, we're going to be there pretty soon in tax. So we're not too far off of it. But if they're in the dark brown or brown zone, which doesn't produce as much N2O because it's drier, the carbon tax for them to recover their cost in the fertilizer through reduced N2O emissions, because they're not reducing their emissions by a whole lot, because they're not producing that much to begin with, it needs to be $350. So this is going to be a little bit out of whack here if we're going to have these people adopt. But the black zone and gray zone, folks, much more of an economic, makes a bit more economic sense. Okay, now we have this issue in agriculture in that we want more yield, we want more productivity, we have more mouths to feed and efficiency and so forth. That requires more nitrogen. From Manitoba, here's the increase in nitrogen annually for major grain crops. Well, if you're trying to reduce N2O emissions and we're using more nitrogen every year, we got a bit of a conundrum. So this is going to be the most challenging part for us for reducing N2O emissions, is the fact that we're going to be using more nitrogen in the future. So we do need to be really smart about this in the practices and that are adopted, and we can still, I think, have the emission reduction even despite not stopping productivity and limiting it from not putting enough fertilizer on the field. So I think that's our biggest challenge really that we have to face. So the long road now, and that's really about looking at carbon neutrality 2050, okay? N2O emissions will need to go down if we assume agriculture needs to be neutral, but it's more than just about just N2O. We're just going to touch on that a little briefly here. Hopefully we can have a good discussion and early sandwich talk more about this. So one of the key things we need is alternative to fertilizer production as it stands now. We can't be using Haber-Bosch forever. It produces too much CO2 from fossil fuels. And the amount of CO2 produced in Canada making nitrogen fertilizer is about 1/5 of the total N2O that's produced from soils. So we need something different. Well, we can say maybe legumes, but there's problems with you relying solely on legumes. They're part of the answer, and this shows Manitoba's emissions of N2O, which kind of plateaus because of a rise in soybean, which fixes its own nitrogen, okay? And really, cereals have gone down, and grain legumes have gone up here, as well as canola. But for Manitoba, it's a special situation that's kind of saving us the soybean in terms of kind of giving us stagnant. Look at this. In 1905, in Norway, hydroelectricity was used to make nitrogen fertilizer. And this is the schematic of the contraption. It's an electric arc in a magnetic field. Nitrogen gases pass through with oxygen, basically air, and the nitrogen and the oxygen combine to produce nitric acid. This is the actual generator here that produces the nitric acid. And this was the plant. 1905, they built the plant, a hydro plant. They didn't have much use for the electricity. So smart people came up with this, producing the nitrogen fertilizer. Eventually, people needed electricity for other things. This wasn't so efficient, and they turned to Haber-Bosch. But today, people are coming back. This is the MIT lab, producing nitrogen fertilizer, ammonia from nitrogen in the atmosphere, and hydrogen produced from electrolysis of water from this little contraption here. And there's a catalyst in here which makes this much more efficient. This is just small scale, but this made a big, big impact because it has the potential for upscaling. In a place like Manitoba with renewables, energy, electricity, it's fantastic. Okay, I know my time is running out. So we're going to have a problem, though, in that anytime we add nitrogen to soil in a slug, particularly in an inorganic form, it's going to be prone to losses, all these types of losses, and they can all produce eventually in the environment N2O emissions. So we're going to be thinking about something differently in how we get nitrogen to plants. In 30, 40 years, we're going to be thinking differently in that delivery of that nitrogen. And I think it's going to be biological, okay? because biological fixed nitrogen isn't that leaky compared to slugging inorganic nitrogen. This is an example here. In nitrogen fixation, nitrogen gas gets fixed to ammonium, goes into an amino acid, gets transferred through the plant and other amino acids and organic compounds. Most of it goes to the seed, and that's what we get. A fraction of it, probably 15, maybe 20% goes into crop residues and so forth that can be recycled. And yes, a portion of that is lost, but a lot less than synthetic fertilizers. And here's an example of what we're looking at. Endophytic bacteria that can produce nitrogen within cells of plant roots. In this case here, they call it a mutant corn, and here you can see the aerial prop roots with this gelatinous material here, which is really a syrupy, sweet material that can feed bacteria to fix its own nitrogen. So there's a massive amount of investment in this by some major companies, some of the biggest agricultural companies in the world in this area, okay? And then there's genetic engineering as well, in terms of thinking eventually down the line, we may even actually have rice and corn actually with nodules and producing nitrogen. So final words, short term for our practices, I believe we have information that can show that we can reduce the N2o emissions. There need to be some incentives to encourage some practice adoptions because they're about environmental benefits, not so much about economic benefits. We do require a carbon market and mechanisms. The long road is going to be biology, biology, biology. We're going to be thinking about nitrogen in a biological form, biological processes, keeping it in organic nitrogen forms, relying on grain legumes, renewables to produce nitrogen fertilizer in the short term likely, but eventually going to organic nitrogen forms through fixation. Yeah, that's it. Thank you very much. I look forward to the panel discussion.